So today we are going to talk about data structures. So let me see if I can. Hopefully my handwriting won't be too horrible today. Okay, so data structures. We've heard this word a lot. We know that it's important in computer science, and we know a lot of people tend to test interviewers on data structures. So data structures in general are, data structures, what are they? They're basically a data organization tool. So it allows you to data organization, management, and storage format. Hard to talk and write. So a data structure is a data organization, management, and storage format that allows us to make efficient access and modification of data. So in other words, data structures is a collection of data values that and the relationship between them and the functions and operations that you can actually do to them. So so data structures hold data, but also have certain rules that dictate how you can interact with this data and how it ends up being organized and stored. And this allows for efficient either data storage or data access based on your needs. So there are many different data structures. Why do we have so many? We have so many because each data structure has a different characteristic that, or different characteristics that can perform different operations at different speeds. So far we've talked about, and we've seen stuff like arrays, kind of close to lists. We'll kind of see the differences a little bit. We've seen objects or dictionaries. So these are types of data structures. They store data and allow you to interact with them in a certain way. So yeah, we need different types of data structures based on the program that we are trying to write. For example, let's say we have a list, okay? We have the list of data that is not in order. So let's say E, C, and B. So let's say this list of characters is not in order, and if we want to add to this list, so this is our data structure here. If we want to add to this list, if we append to the end, this would probably be a pretty quick operation. If we're just appending one new one, it's all you're doing is extending this list. And let's say you're adding F here. So if we wanted to append, this is a pretty quick operation. Let's say we want to add to the front. So if we want to add to front, I think in JavaScript, there's a function called unshift, which adds to the front, or if in Python, you do a like a dot insert and give it the 0 index. So basically, if you want to add to the front, is this a fast operation or a slower operation?
Slower.
Well, how so?
Because it has to rewrite, or it has to create a new area in memory for the whole list, versus the append, it just adds to the end, and because there should already be memory
Exactly.
ready for it.
Yeah, exactly. So this one's slower because if we're adding a character to the front, let's say we want to add Q, this is going to have to take the 0 index. Now the 0, everything has its own index, right? 3, 4. If we want to add this into the 0, we have to shift everything else over. So this has to go here, this has to go here, this has to go here. And so you're not just doing one operation like we did here, we're actually doing as many operations as there are elements inside the array. And if we wanted to, let's say, search an item, search for, let's say, B. How would we search through this list? We would most likely have, sorry?
You can .find.
Yeah, but in general, let's say we don't have access to any of those functions, because a lot of times those functions are implemented using like the basics.
You loop for matching.
Yeah, so you would have to search for this, you would actually have to loop through every single item because you don't know where in the list it is. So because it's an unordered list, because it's an unordered list, you would have to most likely loop through all the items in the list. So searching is a bit slower. Okay, so let's say instead of an unordered list, we have an ordered list. So this ordered list Okay, so for this one, let's say we want to add an item. So if we want to add an item, and this is an ordered list, we probably want to keep it ordered. So this might take some time because we have to look for the exact spot that we need to order to put it in, and then we have to, so this one is a bit slower. We have to look for, okay, well, where do we want to put it? If we want to place it right here, then we have to basically put it in this place and then shift everything over. So it takes not just one operation, it takes quite a few. How about if we want to search? So if we want to search for an item, let's say search for E. Searching in an ordered list is faster because since it's ordered, this is one type of algorithm that you can use for search. You basically access the middle point because we have access to the indices, right? We know the length of the list and we can say, okay, let's access the length of the list divided by 2. And let's say that's 2 because it's 2.5. So index 2. Let's see, is E larger or smaller than D? E is larger, so we would check only the second half, and then we would do the same. We would say, okay, let's access the middle point of the rest of the indices, and let's see if we find it, and it found it. We'll learn more about time complexities and stuff like that on Thursday, but basically, this is a faster search than having to go through every single item. It tends to be like quite a bit faster based on an array list. So this is just to demonstrate that choosing the data structure can affect your computing speeds based on what you're looking for. So if I value search, so if my program has a lot of searching and I need to find things very efficiently, then you would probably want something ordered because you can search it faster. But if all you care about is to store data and you just want easy appends, then you can use an unordered list and just keep appending to the end, and that would be it. Any questions? All right. Yeah, so learning how to choose the appropriate data structure for a problem is a pretty big part of solving problems efficiently in programming. And I think there was a quote that said, bad programmers worry about the code, good programmers worry about the data structures and the relationships. And that was Linus Torvalds, who wrote the Linux operating system, and I believe Git, if I'm not mistaken. Okay, so let's talk about actual data structures. So first we have arrays. This is the simplest, what is it called? I think it's called a linear data structure. So arrays are not exactly JavaScript arrays. JavaScript might implement some sort of an array in the backend. Not sure exactly how it's implemented, but arrays in computer science are literally just a list of data that is continuous in memory. So let's say I define an array or a list, and this array starts at like memory 0077, something like that. So this one would be this. So this one would be 00078. This one would be 9. So that's how we are able to usually access arrays with indices. So an array is just a list of similar data that is continuous in memory, and you typically have like a certain set amount of data that is preserved for an array. And if you want to insert more items, you would have to create a larger array somewhere else in memory, copy everything over. So like, let's say I want to add more to this list. I created a new one that's much larger. I have to copy over all the items. So let's say this just has numbers or something like that. So 3, 4, whatever. And then the next ones become empty, and then we can delete this one. So yeah, arrays are a pretty basic data structure that a lot of other data structures are built off of. And having all of these continuous, having all the data in continuous memory slots makes searching and retrieving the items pretty much faster, because you can pretty much start at the top of the list and just iterate through it one by one, like we do with a for loop. Or you can just access each index by saying like, give me, let's say this is array A, you can just access it by A of 5. Internally, A starts at this address and it just adds 5 to it, and it knows exactly where that data is. Any questions about arrays? Okay. So the next data structure we're going to talk about is called a stack. So a stack is a data structure that only allows adding to the top of the stack, which is usually called pushing, and removing from the top of a stack, usually called popping. So think of a stack of pancakes. And if you want to eat the pancakes, I know you can cut through them, but let's say you can't cut through all the pancakes, you would have to eat one at a time. So the top one is the one that is the only one that you can remove. And then if you remove that, then you have this exposed. So stack is pretty much that. It's typically it's built with an array. You can also build it with a linked list, which we'll talk about in a bit. But think of it as an array that is stacked like this. So this is the 0th index, and this is the top up here. So whenever we add to the stack, so when we push, so let's say we want to push A would go over here. Let me make this drawing a tiny bit bigger. There we go. So, oops. So every time we are pushing something, it goes above it. And when we want to say pop is the operation that will take, so top will be pointing to the last element. So it will just access the last index of the, what is it called? So yeah, the stack knows about what the last element is. Pop will just remove this element and then return it. So this one will return C. So yeah, so a stack, think of it as kind of like the lists in Python, but if you can only use the push and pop operations. So this data structure specifically allows you to process items last in, first out. And yeah, and typically in the API of the stack, so the functions that are allowed in a stack are push, pop, size. So size returns how many elements. And sometimes you will also see peak, which will what is it called? Return the value at the top. Push, what does push do again? Someone? Sorry?
It adds it to the top of the stack.
Yep. Add to top of stack. What does pop do?
Removes from the top of the stack.
Yep. Removes from top. Awesome. Any questions about stacks? Okay. Okay, so another data structure that is pretty similar to stacks is a queue. So a queue is similar to a stack where it usually uses like an array as an underlying data structure. But the difference is it doesn't add to it's not like last in, first out. So it's not adding to the top and you can only remove from the top. Queue is more like a restaurant queue. So let's say this is the beginning. If we add to here, then we would have to remove from the front. So if we are, so let's say we have A, C, E. So we are appending to the end, or in queues, you usually have a function called unqueue or inqueue. And then to remove from the queue or remove from the front, this is called dequeue. Okay, so we have NQ and then DQ. So think of a queue as like a list at a restaurant. There's a wait list on a restaurant or at a restaurant. And if you're the first one there, then your name gets written first, second one, third one. And as the tables start emptying out, the first person gets taken off and gets seated. And then the second person gets taken off and gets seated, and so on. Yeah, so typically queues are, they have, like I said, the two functions. So unqueue, dequeue, I forget if there's other ones. There might be also a size similar to stack, just to know where, like, how much the size is. Okay. So typically with these functions, when you're trying to implement them, you make a class. So let's say class stack. And then in your initializer, you will hold on to a certain data structure that will actually hold your information. So in this stack, what do you think the best data type we should use to hold our data?
No, right?
Sure, yeah. We can call it a list in Python. So this is just like a Python list. So if this were code, I would say like self dot, I don't know, you can call this anything, like maybe base. This is our base data structure. And this is just an empty list. So if we're defining a function that is push, what are we doing with this function? What are we actually changing here?
Adding to the end of base.
So it would be base dot, what's the function name here that we have access to in Python?
Append.
Append, yeah. So base dot append. If we are doing pop, what can we do to get the item? So if we're calling pop, it's going to get an item, right? So how are we retrieving it?
Base.pop.
Yeah. So you can do base.pop. If we had restrictions and we didn't actually have a pop function that's written for us, we can do base dot, I think get is a function where you can specify the index, but basically you can retrieve the last item. So something like that, or base at -1. And then you can delete that one. And then you can return it. So return item. But before we do, we would have to remove it from base. And then we would return the item. So this is typically how you would implement these things. I'm not going to show you how to implement all of these because that is our those are our exercises for today. But I just wanted to give you a little hint here. Yeah, any questions about stacks, queues, and arrays?
Yeah, I had a question. So the concept of stacks and queues, we kind of make it ourselves. There's like, I'm trying to think of how it was going to look like if you try to use a stack or a queue. Like, I don't know if you make it yourself. It looks like you're making it on the side right there.
Yeah, so stacks are typically not built in. They use data structures, data types like a list. So let's say I'm trying to build a stack in Python. A stack is basically a list that we're using in a very specific way. Same with a queue. Queue is a list that we're using in a very specific way. And that specific way is how we are adding to the list and how we are removing from that list. So if we have a program that is using, that is implementing a restaurant wait list, we would probably use a queue. However, if we're using something like, trying to think of a more practical example, but the only thing I can think of is there's the parentheses exercise that we had done last week, 2 weeks ago. Basically the balanced parentheses, where you are checking if there are parentheses that are balanced. If you're adding them to the stack, so if we had a stack, if we pushed this one here, and then we pushed this another opening one here, if we get to a closing one, then we're like, okay, we have a closing one. Let's see if we remove the one before, if it matches, if it's like the complementary one, that means it's correct. So we do a pop. And then this gets removed. And now we're back to here. We were here, right? And then the next one is up here. We check, we can pop this one off because it's the same, or it matches, sorry, it's not the same. And that is how we know that it's balanced, because our stack ends up empty. So stacks are used when you only need to add and remove from the end. So yeah, these are all specialized ways of using something, and you will use the specialized ways based off of the specific problem that you're trying to solve.
Oh, I just had a quick question for you. Is there some sort of like guiding principle that we can use to know, like, oh, in this instance, it's best to use a stack, and in this instance, it's best to use a queue, just so like when we're solving problems, is there like some sort of queue that we would know to be like, okay, this, in this case, you would use this or this?
I think typically when it all depends on where, if you're adding data in a list sort of way, so like adding it one by one, you kind of want to see, do I want to remove only from the end and add to the end, or if I want to simulate a queue type where I am adding to the beginning, I'm adding to the end, so the list keeps growing, but when I'm removing from the beginning. So your problem is your guiding principle, pretty much. Your problem and how the data structure operates. So if you know how it operates, you know that a queue will enable you to add to the end and remove from the front. If you have a problem that needs a list that will add data to the end and remove from the front, then that's your queue to use a queue.
Hey, yeah, we're going to talk about this a little more Thursday when we talk about what's called big O or complexity analysis. But basically every data structure, even if it's not obvious right away why you're doing it in like this push pop sort of way, or I mean, data structures tend to have these very specific ways you use them. And the whole purpose of it is that once we do the big O analysis, we'll see that you get certain guarantees with certain data structures versus others. So basically those guarantees plus doing a lot of leak code type problems, usually by topic, will teach you, oh, this is an example of a situation where just a queue should come to mind. It's hard to teach that intuition, but you'll find that once you're doing leak code type things, they do organize it to say like, hey, here's a bunch of stack problems, and you'll see problems that, you know, sort of lean towards a stack, and it will build up your intuition around that. Yeah.
Great advice. Thank you, Benjamin. Any other questions? Okay. Let's move on to linked lists.
just make sure a lot of these are going to be data structures that we have to implement ourselves that aren't necessarily built into, I guess, most languages.
Correct. Yes. I believe a lot of them have been built into libraries, but especially for today's exercise, you are like, you're going to implement them yourself. And a lot of people, not a lot of people, but there's a good amount of interviews that either expect you to know how to build one, like a tree or something like that, or at least like use its functionalities, use its methods to like iterate through them, or you just have to understand how they're structured pretty much.
Is there a reason why they're not built in? Are they just uncommon, or why is that?
I don't know. Some of them are, I don't know. Benjamin, do you know?
Yeah, they tend to actually be built in, but not at a level you're expecting. So something that's important to recognize with data structures is that a data structure is just an idea. It's not an implementation. So the idea of a stack or a queue could be implemented in any language, but that doesn't mean it's necessarily going to have sort of what we would call top level support in something like Python. So in Python, your arrays are powerful enough that you can use the array to create a stack or use the array to create a queue. So it's not actually defined for you as, oh, this is a specific thing that you have access to, because what Python calls an array has access to all of that. It has methods on it, it has all that stuff. But that said, generally, whatever data structure a person might want to be working with, there's going to be some library that sort of standardizes things and makes it, you know, work efficiently without you having to think about it. So the average developer, even very high level, is not generally writing their own data structures in the sense of like, yeah, kind of you have these sort of standard ones and they're going to exist in certain major libraries. Like in JavaScript, there's this library Lodash, and that tends to be where you have access to all those kinds of like useful data structures. But yeah, this is getting meandering at this point, but what can I say? I just want to make sure I'm answering the original question.
You did.
Yeah. Okay, good. All right. Back to Zainab.
Awesome. Okay, so linked lists. So we talked about arrays. We know that if we define an array like A, B, C, it creates continuous slots in memory that contain those data pieces. Linked lists, on the other hand, are a list of objects that can live anywhere in memory, but they are linked to each other in a way that you can iterate through them. So you can start at the beginning one and go through them, but they don't have to be in the same spot in memory. So arrays are pretty powerful and very useful, but sometimes you don't know how large your array is going to be, and you care a lot about space, you care about saving the space that is used during your program, or yeah, so it basically, if the continuous model of saving data in a list does not work, linked lists are here to help. So each of these little objects is called a node. So a linked list is made up of nodes, and each node has mainly two properties. So you have a value, and you have a next. So value is going to actually contain your data. Next is going to be a reference to the next node in that specific list. So reference to next node. Okay. So what does that mean? So let's say we want to store these 3 letters, and we don't want to store them in a continuous piece of memory. So we'll start off with an initial node. This is typically called head. So this is our head node. So our linked lists contains a head. And this head is a reference to a node. So this is my little node here. So my node has a value, let's say A for the first one, and then it's going to have a reference to something else. Typically, if there's only one item and we don't have a list yet, so each node will have a next value of none. So I'm just gonna signify it by this. So none or null, depending on the language that you're using. But basically, this is a linked list with one item. Let's say we want to add B, we want to add another node. So then we create a new node. This node will contain the value B. It will point to nothing next because this is a new node. And we will access the header or the head node, and we will turn this none to a pointer that points to the new node. And we keep chaining these. So if I want to add one here, I can just remove the none, point it to a new node that I've created that has a certain value, and so on. So it becomes a chain of little objects, pretty much. And these objects can live anywhere in memory. So if this was your entire memory list, you can have A living over here, B is living over here, and C is living over here. And since everything is starting from the head and you are traversing pretty much using these references, so you keep going down the list, it doesn't matter where these actual nodes are stored in memory, you have a reference to it. And that allows you to, what is it called? To be able to traverse through the list itself. Yeah, so linked lists, there are typically, this is a singly linked list. So each node is linked through one, pretty much like a one-way arrow that links this is that. A doubly linked list it kind of is in the name. So a doubly linked list will have your value. It will also have it will have a previous and it will have a next. So each one, so the first node is going to have nothing for the previous, but then it will have a next pointer to the next node. So I'm actually going to draw it like this. B, so this is next, this is previous. So this previous one will point to this entire node over here, this one here. And then same if you keep chaining them. If there's a previous node, this is going to point there. The next is going to stop here because it's the last item, and so on. So this previous value in the doubly linked list, it's helpful when you have a need to not only traverse the data this way, but also you want to traverse back. So these linked lists can be used for other, like to represent other data structures. So like a stack, I could easily build a stack with a linked list. What are the rules for a stack?
Push, pop, and peek.
Yeah, so the rules are I can only push to the end, and I can only remove from the end. So with a linked list, I can easily do that. I can just choose which end I'm talking about. So if I want this to be the beginning, so this is my so let's say I have a resource that will allow us to see these. Let's see, where is linked list? Okay, so stack implementation with a linked list. Okay, so here, let's say I have, like I want to push 4. I push it. So now this is head or top. This is basically the reference to my list itself. So this is the header of the list. So I pushed 4. Cool, it did what it needed to do. I push 5. Or sorry, 6. It adds it to the beginning. I push 7, let's say. It adds it to the beginning. So this is essentially the top of the stack. If I want to pop, what is it going to do? It's going to remove this item. So if I do pop again, it's going to remove this item, move the pointer back here to the item afterwards, and then it's done. So if I want to add something else, push, you can push more stuff. So here, and pop.
So for the linked list implementation of a stack, does it actually open like the item for overwriting or the data for this data is now available for use, or does it just remove the reference to that item in the linked list?
No, it removes it and returns the actual value, and then so here when we pushed, it is a little fast, so maybe I'll slow it down. So I have 7, and then I pop it. That's a little too slow. Let's do a middle. Okay, so if I do pop, it popped the value 7. It held onto it. It repointed it. It's going to now remove this and then return the value itself.
Got it. Okay, cool. Thank you.
Yeah, so it's going to do pretty much the same thing as we would do in a regular stack. And if we looked at the array implementation, like we expect, if we push a value, I'm going to move the animation speed up a little bit. Oh no. I'm getting my chart here real quick. There we go. But yeah, this is just, if we push, it just pushes it onto the next one. And if I want to pop, it pops from the top value. Okay, let me now show you how queues look. So I want to in queue. So in a queue, you sometimes have a head and a tail, just so it knows where the beginning of the queue is and where the end of it is. So if we're adding more, it will add it to the end. That was a bad example because I added the same one, but it keeps adding it to the end. And if I want to dequeue, it's going to access the first one and it's going to remove it. If I dequeue again, it's going to access the first one and remove it. If I in queue, it's going to add to the back. If I dequeue, it's going to add to the front or remove from the front. Questions on those implementations? Awesome. This website is also linked to at the bottom in the resources. This is pretty helpful. And we'll come back to here and see a few more visualizations in a bit. All right.
I've got a quick question. if you
Yeah.
don't mind. Having done a couple of these in LeetCode, it was very confusing how they wanted us to kind of represent it. Next, should it actually be equaling the node object of the next one? Because that gives it the reference location.
Yes.
Is that right? So then when you say next dot, whatever, you can access that next node.
Exactly. Exactly.
I wasn't
So-
ever sure I did that right. So
Yeah.
Okay.
So typically with linked lists, and you'll also see this in the homework today, we have two classes. We have a class that represents the list itself. So linked list. And then we also have a class that represents the node. So each node only has these two values if you're doing a singly linked list. So it has value and it has next. You can initialize the value with whatever data value you have. This one can be none when you initialize it. So then when you are creating your linked list, data-wise, this one is holding on to head, which is going to be a reference to a node. So head can start off either, so it starts off as none. When you initialize a new linked list, it can be empty. But then if we insert or add, I guess, or add. So this can be this function. So when we're inserting or adding to the linked list, we are creating a new node. So n equals node. Let's say we initialize it with data 7. So now we have n is a reference to a node that has data value 7, and then it has next value as none. So when we are so if we want to hold on to n inside of our linked list, because this is the first value, we would just say head equals n. So head is the reference to the first node always. And then each node will hold on to the reference to the next node. So in your linked list, your head is just pretty much a little pointer to the nodes themselves. So this is head. And then every time, so now I have a 7 here and I have a none. If I were to insert another node, there's a few more operations that we would have to do instead of just saying head equals n, just because we would have to go to the next one. But basically, you would be adding to this. So you would say head, which would reference this one. If you say dot next, it would be referencing whatever is supposed to go here. Then you would say head dot next equals a new node that, let's say we want to initialize with 8. So now there's an 8 that is none. And if you wanted to access the one afterwards, what would I do? So head dot next gives me access to this one. If I do another dot next, it would go to this one. And then you can do node. We don't typically, so if we want to do that, then this next pointer will now become a pointer to a node that has 9 in it. We don't typically chain the next like this. We will hold on to a variable, let's say current or current pointer or something like that. We started off at head, and then we kind of loop through checking. Like we keep going current dot next. As long as current dot next is not none, we keep traversing until we get to the end of the list, if we wanted to get to the end of the list. But yeah, questions on linked lists?
Yeah, do you typically only use linked lists in queues and stacks?
No, so queues and stacks only kind of make strict rules around where you can add and remove from in a linked list, but you can use linked lists in any way, in any with any rules. So based on your use case, some people create linked lists that just add to the front and just remove from the front. I guess that would be a stack. Some people want to keep an ordered linked list. So so let's say this one is in order and this one was an E. So I wanted to insert C. I would have to kind of loop through, find it, and then I would insert C over here instead of the E. I would put the next pointer pointing to this, and I would move this pointer instead of here, it would now be pointing to here. So this is actually a pretty big bonus for linked lists. If you're holding like sorted data, an actual replacement is so much better. It's so much easier than having to insert something into an ordered list, like an array, because if you insert something in the middle, you have to, or in the beginning, you have to move everything over. But here, you're just changing a value of a reference. You're just changing what this next is and what this next is. And that is how you insert a new node in here. Instead of if you were inserting something into a list, you would have to insert it into this space and then move everything from this space on one index over, pretty much. Yeah, did that help? I kind of talked a little too much about it, but
No, that was perfect.
awesome. Other questions? And linked lists are like not that simple of a topic, but they're also not too horrible. Hopefully when you're starting to implement it and you're playing around with traversing them, it'll start making a little more sense. But definitely for these more complex data structures like linked lists, and later we'll talk about trees and stuff, when you are writing code for it, drawing it out like this, just to understand where things are being inserted, where things are, how you're traversing and going from one node to the next, it's an extreme help. So I would recommend having like a piece of paper next to you that you're just kind of drawing out how these things are and how you want them to look, and then you can write the code for it. But yeah, so linked lists as a summary is a way to store data that is connected, but doesn't have to be in a continuous stream of memory. So you can hold on to objects and then connect those objects in a line, pretty much. Any last questions? No. Okay. See, it's 9:50. Let's take a little break. I'm gonna stop.